We in the local hour angle when in east longitude, we add the to obtain the meridian. Know that it is the same. If the LHA is 100 on 80 degrees, the angle is 360 minus LHA, and it is therefore east. The position of a body on its hour inclination is similar to latitude on the Earth. It is measured this way if the declination is north, and this way if the declination is south. Note how the two coordinates, declination and Greenwich hour angle, locate the position of a body on a celestial sphere in the same manner that latitude and longitude locate a position on the Earth. Pass half a great circle from the zenith through the body to the nadir. This circle is called a vertical circle. The circle is perpendicular to the plane of the horizon. A body is located on the vertical circle by its angular distance of the horizon, which is called its altitude. The zenith between the north direction of the meridian of the observer and the vertical circle through the body is called the altitude. As this is before navigation, let us examine it in detail. Let us consider a body which is east of the observer meridian and pass its hour circle and vertical circle through it. Note the angle which is formed at the zenith between the upper branch of the local meridian and the vertical circle through the body. This is the azimuth. Rotating the celestial sphere until the zenith is at the center of the diagram, we can see that the azimuth, Zn, may also be defined as the arc of the celestial horizon, measured from the north point of the horizon N, clockwise to the vertical circle through the body, from 0 to 360 degrees. This angle Zn is important, you will remember, because it is the bearing by which the navigator plots the direction of the body from his assumed position. When the observer is in north latitude and the body is east of the local meridian, the astronomical triangle is PZM. In the solution of the astronomical triangle, one of the elements which we compute is this angle within the triangle called the azimuth angle. This is to distinguish it from the azimuth Zn, which is always measured from the north point of the horizon. In this case, with the observer in north latitude and the body east of his meridian, we see that the azimuth Zn and the azimuth angle Z are identical. Now, if we move to south latitude, keeping the body in the same position on the celestial sphere, we see that the azimuth angle is measured from the new elevated pole, PS, to the eastward to the vertical circle through the body. That is why the azimuth angle is named south like the latitude and east or west like the meridian angle. In this case, therefore, the azimuth angle is south 168 east. We must subtract this azimuth angle from 180 degrees to find Zn, which equals 12 degrees. With the observer still in south latitude, watch the body as it moves westward on its diurnal circle to a position west of the observer's meridian. Here, the azimuth angle is this angle. To determine the azimuth, add 180 degrees to the azimuth angle, and we have Zn. Moving again to north latitude, keeping the body in the same position on the celestial sphere, the azimuth angle is this angle. But now it is named north and west, because the latitude and meridian angle are north and west. To determine the azimuth, subtract the azimuth angle from 360 degrees as shown. We have now seen how the azimuth is affected by the position of the observer on the Earth. Don't forget that it is very important to name the azimuth angle so that you can tell whether or not it is necessary to subtract it from 180 or 360 or add it to 180. In reference to the tables which you will use to compute azimuths, it is well to remember that the term azimuth is used in the tables, but the angles tabulated are really the angles inside the astronomical triangle. That is, they are azimuth angles, not azimuths. To sum up, azimuth angles are named like the latitude of the observer, north or south, and like the meridian angle, east or west. Now that we have seen the effect on the azimuth angle when an observer changes position, let us next look at the effect of different declinations. For the purpose of illustration, it is convenient to change the bodies in declination on our diagram. Of course, this never actually happens as illustrated, for the declinations of heavenly bodies, even of the moon, change very slowly during the course of one day. As we deal with different values of declination from north to south, note that this distance from the body to the pole is the polar distance, or 90 degrees minus the north declination, and that it increases as the declination of the body decreases. At the same time, observe the azimuth angle increase. In this diagram, the azimuth angle becomes 90 degrees before the polar distance, which does not become 90 degrees until the body is in the equinoctial. With the body farther into south declination, the azimuth angle has increased, but the polar distance is now equal to 90 degrees, plus the south declination. Now look at the problem with the observer in south latitude. The south pole is above the horizon and is therefore the elevated pole. The planet, which we have just seen from north latitude, remains in the same position on the celestial sphere, but the polar distance will be 90 degrees minus the south declination. Now, changing declination to northward again, the azimuth angle is larger, and the polar distance has also increased. Across the equinoctial, the declination is north, and the polar distance is 90 degrees plus declination north. If the body is west of the local meridian, a similar effect takes place. The body moves across the local meridian on its diurnal circle to a position west of the meridian. The distance from the body to the pole is equal to 90 degrees minus the declination north. With the declination less than before, note that the polar distance and azimuth angle are greater. Now, with the declination 0, the polar distance is 90 degrees. In south declination, the polar distance is 90 degrees plus declination south. Further south, the polar distance and the azimuth angle have increased still more. The only effect the meridian angle has is to place the body either east or west of the observer's meridian. Watch the meridian angle change as the body moves westward. As the body crosses or transits the observer's meridian, note that the meridian angle is 0 and the azimuth angle, in this case, is also 0 degrees. When the declination is less than the latitude, or of opposite name, then when the meridian angle is 0, the azimuth angle is 180 degrees at the time of transit. The same relationships hold true for an observer in south latitude. Now let us combine the factors we have just examined and see what we have. This angle at the pole is the meridian angle, and this angle at the zenith is the azimuth angle. Here we find altitude, declination, and latitude. We see sides of the triangle are cofunctions equal to 90 degrees minus latitude, 90 degrees minus altitude, 90 degrees minus declination. That is to say, the sides are co-altitude, co-declination, and co-latitude. However, co-declination is frequently referred to as polar distance, for, as has been shown, polar distance equals 90 degrees plus or minus declination. The principal problem of celestial navigation is solution of this triangle. These elements of the triangle, co-declination, co-latitude, and meridian angle, are known or assumed. Note how the celestial triangle can be projected on the spherical surface of the Earth. Now we are able to appreciate why we can fix a ship's position by solution of the astronomical triangle. Computing Zn gives us the bearing of the geographical position from the assumed position. Should our actual position and our assumed position happen to coincide, this would be our line of position, and the computed and observed altitudes are equal. But if our actual position is at F, then our true line of position would be this one. You can see that it is also perpendicular to the bearing line to the geographical position. Because it is closer to the geographical position of the body than the assumed position, the observed altitude is greater than the computed altitude. This distance along the bearing line, AP-GP, is the altitude difference A, which you will remember is the difference in minutes between the computed and observed altitudes. To show why the altitude difference can be directly measured in miles, note first that the line AP-GP is a segment of a great circle on the Earth. This line is the bearing between the assumed position and the geographical position of the body. Now, if we compute the altitude of the body from our assumed position, we find it to be hc. However, upon measuring the altitude, we find it to be ho, which is greater than hc. Subtracting the two values, we find that the altitude difference is 3 minutes. As the star for which we computed the altitude and the star we observed are the same, it is evident that our assumed position is not correct. To make the observed altitude fall upon the star, we must move closer to it. Now the observed altitude is correct for the star, and we find our actual position is here on this line of position. As we have moved 3 minutes on a great circle, the distance must have been 3 miles. Our problem then is the solution of an oblique spherical triangle, where we have given two sides and the included angle. To find this side, the co-altitude, and this angle, the azimuth angle. The solution of the astronomical triangle by modern methods is usually based on dividing the oblique spherical triangle into two right spherical triangles, as right spherical triangles are more readily solved. The astronomical triangle can be divided into right spherical triangles in two ways. First, by dropping a perpendicular from the position of the body, M, to the local meridian, PZ. This will give us two right spherical triangles, PMX and ZMX. In this triangle, we have the angle T and the sides MP, the co-declination or polar distance, PX equal to co-K, and R, the perpendicular distance from M to PZ. This triangle has the angle PZM, called the azimuth angle Z, and the sides, co-altitude, R, and ZX. ZX is made up of the algebraic difference between K and the latitude of the observer, L. In the other division of the triangle, we drop a perpendicular from the zenith to the hour circle through the body. This gives us two right spherical triangles, PZD and MZD. In PZD, we have the angles T and Z prime, and the sides, co-latitude, PZ, DZ, which is called R, and is the length of the perpendicular from Z to D, and the side DP, called small b. In this triangle, there is the angle Z double prime, and the sides MZ, the co-altitude, DM, called B, and the perpendicular R. It can be seen that capital B plus small b is equal to the co-declination, and that the azimuth angle is equal to Z prime plus Z double prime. By applying Napier's rules for right spherical triangles, any of these right triangles can be solved. There are a great many methods of navigation. All are good. Some are more brief and direct than others. The great majority of these short methods divide the astronomical triangle into two right triangles, pre-compute the essential data, and tabulate them in some such fashion as this. Thus, the solution of the problems of celestial navigation is made easy, simple, and direct.